The objective today is to describe in great detail how bits are used to make computers work. So by now we all know that a bit is the smallest possible unit of data. When a computer is using a bit, it always means on or off. When it comes to physics, though, a bit is made to be above or below a certain threshold. So for wires, an on bit is usually above 1 volt. Think right, share what is the difference between the computer concept of a bit and the actual electrical wires. For flash storage, an on bit is around 1,000,000 electrons. Isn't that crazy to think about? Roughly 1,000,000 electrons will create an on for flash storage. For fiber optics, an on could be around several billion photons per second. In all of those cases, if the measurement drops below that threshold, the bit is off. Think right, share. Were any of these surprising to you? Computers have a lot of circuitry to make sure that anything carrying a bit is either way above the threshold or way below. That way there is no maybes, so that bits are always definite on or definite off without any confusion. From bits to encoding. When you think of encoding, maybe think of the word naming. You can name a puppy, and that thing will know what its name is, so when you call it, it'll come. In computers, if you encode something, you can call it as well, or bring it up just by saying its name in bits. Context is everything, though. If you start shouting Fido in an empty room, he'll probably never show up. An optional think right share here is how far can you take this analogy? To go a little bit farther, just to help you out, if you call something and the computer is not in the right context for that, if you've opened up a Wolfenstein video game and you're trying to call a certain action, like push a key that you normally would push in another video game, that key is going to do nothing. So there is no encoding for that particular key. So to keep going with this optional think right share now, you can use anything we've talked about in terms of ASCII, games, software, even the internet. Try to make an analogy from that. There's a simple formula for determining how many bits can be named without a given number of bits. 2 to the number of bits will do that for you. So with 3 bits, that's 2 times 2 times 2. We can count to 8 with that. What if we wanted the computer to be able to name every letter in the alphabet? Well, 2 to the 4 is 16. That's not enough letters. So we would need 2 to the 5th. That's 32, because there's 26 letters in the alphabet. That's enough. It seems like 5 bits is a good number of bits. That could be useful, but it's not enough, and here's why. English, we use capital letters and lowercase. Some languages do not, like apparently Korean. You may have noticed that the number of values a computer can use for various numbers of bits is always an exponent of 2. People like exponents of 10 because it's easy to do math that way. But we're talking binary, so we will use exponents of 2. Computers work best with these exponents. If we had 32 letters in our alphabet, then 5 bits would seem to fit even better, but 5 is not an important number to computers. It makes more sense to actually round this up to a multiple of 2, which is why early computer engineers chose to use 8 bits so much that they gave it a name, byte. And on top of the letters of the alphabet, you have all these symbols on the keyboard and all these other things that would need to be encoded for the computer to understand what you're trying to do when you push these keys. So I feel like this dog analogy is a comforting abstraction to understand how encoding works. Also, ask me about my switch analogy. I like to think of bits and connecting bytes as switches to bulbs, that is pixels. It may not be spot on, but it's a comforting abstraction for me to think of it that way as well. At the end of the day, we're looking at a screen, whether it's on our phone, our television, or a laptop, and that screen has pixels, and those pixels are lit up a certain color. Now you know what data is, and so code is easy to explain. It's just data. That's all it is, really. The reason why it's different than other data, though, is because a CPU interprets it as instructions. The computer receives instructions, looks for the data to use the instructions on, and ta-da! Did you ever notice that ta-da is just data in a different order? So for example, all zeros in a number 1 may just mean you're supposed to add something. If it's all zeros a 1 and then one more 0, that could tell the computer you're trying to subtract something. So now memory is organized on a computer by something called memory addresses. Generally speaking, the addresses are sized by bytes. So if we wanted to access memory location 5 or whatever, we could store that as 0000101. Think right, share. Remember padding? How much padding is in the above binary number? Let's go back and do something now that we have instructions and a way to store information. Now we can say something like this. Add the number at location number 5 in memory to the other number at location 7 by breaking it down into add memory 5, memory 7, which is really just 00001, 0000101, 0000111. I highly suggest this game Circuit Scramble to help you understand how it's a combination of binary that leads to a specific action. I'm currently at level 84. If anybody can get past that extra credit, let me know or let me see. So at the end of the day, that's all the computer is doing. You're going to give it an instruction and then an address to look at and another address to look at in order to fulfill that instruction. It's going to be more complicated later on, but this is just a good fundamental concept for you to know. So your DOL, what are the ways bits can be used to encode something meaningful? Okay, and if you struggled with this, I'm going to supply you with an exemplary answer here. Bits can come from a variety of sources, such as photons in fiber optics, magnetism, or a level of voltage on a wire. Once these bits are received, they can also mean a variety of things, such as a letter, number, picture, or sound. They can also represent instructions, such as addition or subtraction. These are known as opcodes. The act of coding or programming is simply the combination of instructions with 2 or more numbers, letters, pictures, or sounds, or creating an environment where a user themselves can combine numbers, letters, pictures, and or sounds. For example, calculators, text editors, music, movies, and or games. So if you really struggled, you could go ahead and use this answer to put into your own words and offer me a great explanation for your DOL today.